Stanford University.
Welcome to the seminar on People, Computers, and Design. I'm Terry Winograd. Next week, we have actually a speaker who's... Sorry. Next week, we have a speaker which is actually a continuation of some of the things that you're going to hear today. Shritak Patel from the University of Washington is also looking at the ways that you can use multiple sensors as a way of interacting with the control and the computing in your home. He's looking at a whole range of things, including your electricity grid and so on. So it's a kind of interesting expansion out from the kind of work that Hamid is doing that you'll hear about today on vision sensors and its use for interaction in ordinary environments. Hamid is a great example of what I always say. Students come to me and they say, prospective students, and they say, what's going on at HCI at Stanford? And I say, well, I'll tell you what's going on in our group, but I really don't know all the other departments and all the other places around campus because there's so many where interesting HCI work is going on. So I fairly recently discovered that this project was going on in electrical engineering right across the street from us. Then I wanted to find out more and give you a chance to hear about it. So Hamid is in the electrical engineering department. We'll be talking about his project on vision and sensing.
All right, thank you, Terry, and very pleased to be here. I'm going to be talking about some of the ideas, concepts, and embodiments of some of these concepts in our labs over in the Packard building, called human-centered vision systems. We try to use technology, multi-camera technology and algorithms in order to investigate whether we can create some sort of HCI connections for people or develop context-aware and user-centric applications, trying to see whether there is any potential for taking cameras, which sometimes are regarded as invasive sensors, to people's homes, while giving them assurances about privacy as well as creating some valuable applications so they can use them to their advantage. Here's, well, to give credit to my students, my collaborators, and some of them are in Europe. Let me show their names and pictures, and then briefly talk about the geometry of our labs. This is a wireless sensor networks lab, which we started about 6 years ago. And at that time, we were thinking about how communication between cameras and this distributed processing of information across the network could be put together as a platform for creating vision-based applications that where cameras may not necessarily be connected to a central processor, but they start processing in their location, and then information would be fused across the network for high-level interpretation decision-making. Some of the applications we have been putting together so far has been calibration of these cameras. There is more to do with when you have multiple sensors than a single webcam. They need to communicate with each other where they are, what they are looking at, geometry, topology that may be involved. We went after doing people counting, occupancy sensing, face detection applications, selecting the best view if you want to stream video from an environment like this size, which camera would be the best one, to automatically select the best view and based on the content, send that information over the network. More recently, we have also put together a different lab, which we call the AIR lab, Ambient Intelligence Research Lab, which looks like a home environment, and we have furniture from IKEA and TV and sitting there. We try to create instances of very adaptive systems that once we know there is going to be a single user using this area, can we create profiles of this user over time, whether explicitly by observing his or her behavior, or again explicitly asking or allowing them to tell the system, the network, what would be the preferences, likes and dislikes of the services we offer them. So there is activity recognition, there is a human interface aspects to this, and then there is multimedia and services that we try to provide, and at the same time we try to be on the side of energy efficiency issues as well. Can we reduce overall energy expenditure by knowing what the user is doing and allocating light sources accordingly, basically, based on the context. So the type of applications we have in mind for implementing and testing there. Some of those, I'm going to show some videos, some preliminary results that we have already from them, and some of them are open questions and open areas for research, and we try to learn while we experiment with these environments. So in the talk, I'm going to be talking about some notions about how we can bring context into vision processing. Vision processing itself is a very challenging proposition. It has been for all that I know from my student time all the way to now. People still are working on segmentation, on background subtraction models that are adaptive, and all the way to the higher level of human pose analysis, body analysis, people location detection and tracking, and even face expression analysis. All those problems are nice and useful, but they're very challenging to do reliably and to do them reliably on a frame-by-frame basis. So what we try to do is to come up with a notion of a context and how we can incorporate different types of context into vision processing in order to add efficiency to the operation of the network and maybe move away from all these robustness issues that have bogged down vision processing from creating applications, real applications out there in people's environments. I'm going to be also at the same time talking about some notions about user-centric design, how these two notions actually work together, go together, maybe one helping the other. If we know about our user, how we can use that as contextual information to feed better processing options into our vision processor, and vice versa. If we have observations, can we create instances where users can come in and give us some information about those interpretations or observation results, and what are like social implications if you want to put people in touch with each other through visual communication channels. What will be the issues, privacy issues, and options that we have to give them? Can we do some of those in real time? That's kind of questions we try to answer. And then on the lower box, I'll list some of the applications that we have in mind. Some of these we have seen in the previous pictures. We're going to go through these almost on a one-by-one basis and try to identify the challenges and opportunities and some of the preliminary results that we so far have on each of those. So vision has been talked about, at least in many different application contexts, premises, from urban sensing to elderly care, assisted living, fall detection, gaming, and vehicular applications, and more recently on retail, advertisement monitoring and measurements of efficiency of ads, effectiveness, and avatarization and face profiling, applications like that, from a single camera, from multiple cameras, from huge number of cameras up there, and some of that is going on still manually, but then people are working on automating these through algorithms and networks. Multi-cameras can add coverage to our area of interest. That's the most basic advantage of having multiple cameras. But we can also think about 3D reconstructions of objects and peoples or actions and events. We can alternatively try to use them to add confidence to whatever interpretation and decision we try to make from these observations. Maybe cameras can have a kind of a role selection combination in the network. One camera can be looking at the overall area, and then another one can come in and look at the face of a person that is interesting to us. So these things can be done, and decision fusion, data fusion, either at the signal level or at a high level, could be interesting topics for research, how to do this distributed sensing and collaborative processing of information. Traditional vision design, many of us may be aware of. We usually think about ideas and put them into tests in labs like ours, where we can actually control the environment pretty tightly. We can control the illumination, locations of the cameras. We can tell our user what to do or what not to do, so we can detect them and write good papers, for example. On the other hand, the issues that are really important and relevant to creating applications, useful applications for people, are how easy these systems would be for a single user to take home and set up or calibrate or initialize, and can we have sort of self-configuration of these systems using purely visual information coming through the eyes of the cameras, not through the hands of the user or technician. And then additionally, can we become aware of preferences, behavior models, and like privacy issues or other contextual information that the users may have, intuitiveness of the interface, how these notions can come into the design of vision algorithms. That's pretty unknown and open-ended area, but I guess being here and talking to you, I think we need a lot of input from many different perspectives onto what is practical, what is doable from a processing and networking perspective, and what is acceptable from user acceptance issue, and what could be done in combination by having these informations. So let's look at how we look at the user-centric design of these networks, at least from our perspective. We tend to come up with an idea of an algorithm or an application. We quickly write a program. Maybe there's a hardware involved. We put it into some tests in the lab, and then we hope that we can now go and make a startup and sell it. Issues that usually some of us may tend to ignore would be how easy would these systems would be to install, how difficult or challenging would be. Does the user have to carry stuff with them? Do we have an unobtrusive system, or it's going to be pretty cumbersome for the user to handle this situation, hardware and all the delicacies of the system? Can we become more sensitive to user preferences or sensitivities or privacy options, and as such? We think the right way for designing an algorithm would be maybe even early on in the first days, when we have an idea, to sit down and think about how we can use our user preferences as context, and maybe their sensitivities in social aspects of these systems as something we have to be very careful about, and maybe provide some redundancy in the design of the system so they can accommodate different types of users. What would be the skill set that we assume the user may have? And then we also starting to think about assistive technology areas where people with limited skills can still be able, should still be able to use our systems. So some of the attributes we have been thinking about, these are very general terms, would be user-friendliness installation and use of the system, self-configuration, automatic environment discovery, which means what cameras will see them in their views when the user puts them on the wall. Can we discover that automatically? Trying to accumulate knowledge from our user and from the environment over time. Can we use the time access to our advantage and become more and more capable of extracting information as time goes on? And then context awareness, privacy we mentioned about, and then how we can also stop at some point and ask the user to query the user to give us maybe explicitly some of their preferences, or maybe with observation we can make some inferences of user preferences by implicit user intervention, meaning we just observe their reaction to a certain service. We're going to see a couple of examples of how we think about these notions in our design. So on the other hand, context is a more general term for a lot of areas, including in vision, which has, I believe, use of context in vision has been it's in infancy. People are talking about it in terms of processing still images to detect objects, for example, cars, or furniture, and could be like one underlying contextual assumption would be cars cannot be on buildings, so they can restrict their view of or their learning method to look on the road of the surface of the road for detecting cars. That level of activity has been going on in vision, but in the plethora of applications that vision tries to handle, from pose estimation to activity recognition to face and gaze analysis, event reconstruction, and also all these surveillance and identification tracking applications, some more information can potentially be embedded into the design of algorithms to be aware and use contextual information when they are available. So the question mark is what kind of things we can already use in terms of context. Let's look at some definitions people have given to context. And context has been more approached or used in like dialogue management systems, where there is a need to create or synthesize a speech. We have to know what kind of person you are talking to create the behavior that they may like. But in vision, and this diagram actually is general. There could be contextual information coming from the environment, coming from the user, which we can call environmental context or user-centric context, which can help the system to accumulate knowledge and then try to guide the processing agents to do the right thing that can solve the problem in light of this context. I'm listing up some of these notions that we have kept in mind. Some of them we have been trying to use, the ones that are underlined. And in the examples that we're going to talk about, we're going to see how we are trying to make embodiments of these notions in designing vision algorithms. There is a different categorization of context, which you can think of as static or dynamic context. Static context could be, for example, domain knowledge. If we know where this camera is going to be set up in a conference room, can we use that information and use that to our advantage? If we know there is going to be a single user that's going to be using this system, can we create a profile of that user and try to use that? Things that don't change or maybe very slowly change. On the other hand, there could be dynamic context which can come to us through sensing the environment, sensing the location, the activities, the actions, the number of people, and if there is a single person, maybe through a user interface, we can give them explicit device to provide us with some contextual information. I like this service and I dislike this service, that kind of interaction with the user. So to briefly look into what we have tried to use in terms of contextual information for vision processing, let's look at a couple of these areas. Multi-camera networks by itself, even though when we started doing multi-camera networks, we're not talking about context. We're looking at calibration, geometry, people detection and counting. But it turns out if we look long enough through the eyes of these cameras, we can use previous information as priors that can help us to do better, even in a single camera case, but more hopefully so in a multi-camera situation where cameras can complement and the redundancy that's in the system can come and help us. For example, we can look at full body analysis from one or two cameras and then face expression from another camera that's located in different location, in different pose. We know that this camera is looking at the sofa of the person. Can we use that to our advantage? And maybe going after active vision situations in which we can also try to anticipate what may be going on based on one camera report. Maybe we should activate some processing in another camera because the user may be walking over there. So this would be to allocate resources in the right places, because if you are thinking about real-time processing, that's already a big challenge and hurdle for algorithm designers. And also try to add confidence to decisions by bringing complementary information from different cameras. So camera priors are mentioned. This is a very simple example. If we have certain instances in the past of our user sitting or reclining on a sofa, and now in real time we try to segment the person from the background. A lot of times we get, thanks to illumination changes and small and big changes in the environment, we can, shadows for example, we can see a lot of wrong segmentation output. But thankfully, maybe if we have kept our knowledge before from how the user would look like when they really sit or recline on the sofa, maybe we can use that information to rule out outliers when we do certain types of processing, even in a low-level vision part of processing. And can also extend this notion to occlusion management, and maybe multi-cameras can help us to get a better bounding box of the person, even if half of their body is occluded. High-level reasoning is an area that has, well, stayed as a beneficiary of sensor networks and vision processing, meaning traditionally the information is fed forward from whatever we call our multi-sensor, multi-camera network. We create instances of observation and we feed them upstream towards an AI module or high-level reasoning module, some logic system that sits there and then sifts through the data, once in a while makes an interpretation and make declaration. We think that we can bring a feedback loop. Actually, maybe more than one type of feedback can come back from this high-level knowledge base, or what we can also call it experience knowledge base, that by bringing some sort of contextual information, maybe we can start doing, give some feedback to individual sensors, how well they are doing, or if they are failing all the time, maybe we should ask them to shut down and don't provide misleading information to us in certain situations. We can perhaps do some task dispatching to the different elements in the network, maybe resource allocation, where to do the processing to have the most impact at this time. And that kind of information can come from immediately processed information, or maybe even from a long-term accumulation of knowledge from the behavior model of the cameras. And that's one way that we think we can try to compensate for imperfect vision processing output. By looking at the history of reports, maybe we can validate or evaluate performance in real time. And then user-centric context, which is a totally different domain of opportunity, would be how to use history of the user that we have sensed or observed in the past to our advantage to provide better services to our user. Can, for example, detect abnormal events if we have looked long enough to a user's home environment and then something is different today from all that information? Can we be more alert that something may not be right with our user? Can we go after maybe comparative demographic information comparison between our user's behavior model and a population that may have the same background, the same status and conditions? Can we analyze and anticipate what may be going on immediately in the future based on what we have seen in the past from our user? And nowadays there is a lot of personal devices that prevail in our environments, from laptops to mobile phones to even smart rooms and cars, information centers in the cars, and multimedia and game consoles that are becoming more and more personal. Can we try to acquire and abstract out and embed some of our user profiles into those devices so they can work more efficiently and more adaptively to the user's need? User preferences can be stated as explicit or implicit, which could be based on the direct query by the system. Can you come in and tell us whether I'm doing the right interpretation? And the user may say yes or no. Or do you like this kind of music? The user may say, I like it or I hate it. Or it could be, another aspect would be how often can the system really interrupt the user, if it's kind of priority-based interactions with the user. And that also very much depends on the skill set that we should assume for the user. Are they a novice or experienced user? What kind of skills they have, and whether the system should interrupt them or maybe to go through a joint learning with the user at the initialization of the system. These questions are open for discussion, and what we are trying to do is to create instances to play with these notions and try to create user profiles for the services that we're going to be seeing some examples in a few slides. And finally, representation mode is another aspect. Users, if you try to create visual communication channels between multiple users, each one may have their own different preferences in what form and shape they may be represented. In a raw video with some annotations, in a kind of so-called voxel model, a shadow model, some colorful shadow, and maybe a synthesized avatar after we can analyze the pose and actions. So offering multiple options to users is one way to create user-friendly or user-centric applications for, at least in visual communication aspect of camera networks. So let's look at, some new potential areas which we can categorize again in a general terms into occupancy sensing when multiple people are present in one environment. And I'm trying to classify this into two different areas because vision processing will be managed and handled quite differently when we know there's going to be a single person or when we don't know and there could be multiple occupants that we need to keep track of or keep track of their interactions. But we can think about in general smart lighting, smart services that could be provided to multiple people occupying in a certain area, or kind of conference room analytics, try to analyze what's going on, the interactions with people. Or if we can focus on a single user, maybe we can run multiple applications from the eyes of the same camera, from fall detection to HCI to gaming to ambient communication, and also a smart presentation as a user-centric approach. So let's try to see where things are at in terms of a smart environment development. These are defined as places that have technology embedded in them in order to sense, to interpret, and to react to events. And sometimes we can also project. If we have some sort of predictive models for stuff going on, we can also project and provide services proactively and predictively. For example, if we know there's going to be a seminar in this room, and because we looked at the calendar, then maybe we can apply air conditioning ahead of time, even before people come in. The situation will be more pleasant for them, the temperature. So these are like smart environments, places that react to events and obviously have some technology to sense what's going on. But then if you put the user at the center of our sort of notion for design, then we can potentially see there is going to be more room for adaptation of these technologies to a single user's likings. And that brings us to the notion of ambient intelligence. Smart environments that have the capability to become adaptive and tailor their services to a single user based on the observations and based on history. And additionally, we can think of putting these different users into contact with each other. This notion of social networks, which is pretty much discussed these days, they would allow for multimodal and pervasive communication links between many people. Each one may have their own preferences and sensitivities and privacy options. How to create instances there by having technology around us and then this adaptivity and context awareness embedded into our design space. So here is a picture I will show whenever we start talking about a certain application. This shows this duality of environmental context and user-centric context that we try to use in some of these applications. I've listed a few that we have been playing with: multi-camera networks as an environmental context, camera priors, high-level reasoning, and then on the user side, knowing about the location and activity of the user, behavior model, preferences, and then representation mode that we have acquired from the user. And these are the list of applications we're going to go through today. So the first one, avatars in general, telepresence, social networks, and putting people in touch with each other based on real-time vision processing and in some form of communication between them. So here we're going to be using what users may have stated as their representation mode, try to combine that notion with this traditional pose and gesture analysis, which is a classical vision problem, to try to create avatars, different types of avatars that people can enjoy being represented by. I'll be running a few videos here and there showing what can be done, some in real time and some may not be real time today. This is based on extractions of shadows or silhouettes from 3 different cameras, which can be done in real time, sent to a central PC, which also in real time puts this voxel representation of the person online. And here we are reconstructing the person's appearance in a voxel domain form without necessarily analyzing what he or she is doing. So different kinds of shadow effects can be added. We can do more. We can also go after methods and algorithms that analyze what the user does, create avatars that are labeled. So we know where the head, the hands, the different joints of the person could be a highly dimensional problem to solve. And some of these methods are not real time at the current technology, but depends on the complexity that you want your algorithm to run at. And for example, it could be like a particle filtering running. I don't know if this one going to pop up. Okay. So it could be, you might want to track tens or hundreds of instances of these particles and then make the decision when you combine them between the cameras. But we can also do some of that in real time. This is an application we did a couple of years ago with a processor, SIMD processor, single instruction multiple data processor from Philips Research. And that runs about 30 frames per second, extracting 5 points of the person's body, the face, 2 shoulders and palms of the hands, and maps them through a wireless link to instances of an skeletal avatar on a regular laptop computer. And here we are using wireless communication, as I mentioned, and some local extraction of information happens in the processor that is next to the camera. So an instance of distributed processing as well. And as we see, this is real time. Then the question becomes what combination or which one of these options we want to choose. Again, in real time when the user tries to make a communication link with another user. Should we go after a method, an algorithm that runs a best camera view selection to send raw video, for example? Or are the users more happy with a 3D shadow because maybe they don't want their appearance to be seen by the person, only their location or action could be transmitted, like in the example down here. And we can, while I talk about it, we can also run this. This shows when the observer user, the second user, is walking around the shadow that came through the network to his home. We can see the perspective also changes, meaning we are also observing the second user's location and try to render the image according to what we expect him to see, if there was a real, like a shadow or a transparent wall between them. Or we can go after more like sophisticated avatarization, avatars that don't repeat what you do, but they have a repertoire that you programmed them before. If I did this action, maybe you should do that action for me. Like in a conference, in a teleconference meeting, if I'm checking email, just pretend that I'm listening to the other side. Things like that can also be very user-centric. We cannot deny that that notion can be done based on some experiencing with the user beforehand and getting their preferences. So here's a picture we keep in mind most of the time, that in vision processing we have access to a tool, a big tool of methods and algorithms, some real time, some not. But in general, we can talk about the pose and activity of a person. We can think about face analysis, gaze detection. Some of this we may be able to do on a frame-by-frame basis, but some applications may allow us to wait a few frames and then make a declaration. Then we tend to take advantage of those flexibilities when they are available. And then a user interface sort of gesture control option, and then also 3D modeling, as I mentioned. And the toolbox is even larger than what's shown here. But then this context interface tries to pick up the right tool at the given time, tries to not only look at the user preferences and availability modes to feed a communication driver up here, which uses different visualization, kind of also building boxes. But they can also look at the data, the recent data, and try to validate whether the data coming from the user is a really good one, or is perhaps shaky, and maybe we should switch our communication mode to a more robust one at this time. Maybe go back to, kind of fall back to a shadow situation when we cannot analyze the pose of the person. So switching between different vision algorithms, it should be done based on the context and preferences of the user. Let's look at a more specific example. Now we think about capabilities to analyze pose of the user. Can we think about a behavior model, adding something more on top of that by asking the user or looking at the user for long enough to create sort of a history and behavior model for him? And we're going to look at this notion in light of a home exercise monitoring application, meaning if you want to allow lazy people or very busy people that may not have time to go to the gym every evening, but they are motivated enough to do a little bit of exercise at home, we give them this flexibility to still be monitored, measured, and maybe socially connected to others. And it turns out that both of these factors independently, they are big motivational factors for staying on good routines such as exercises. Being monitored and measured, that gives a person an impression that is better, that I beat myself over like yesterday's measurement. And having this social connectedness creates this atmosphere or competition, and being connected to a coach or trainer or somebody next to them is also a positive motivational factor. And here's a big picture of the design. We are thinking about, again, multiple types of avatars to extract and represent the user by. At the same time, we try to create to obtain measurements of the user to try to give them local feedback and instructions and put them into a sort of a gaming situation that they have to look at the progress report and then maybe do better next day. So the connection with the coach is mentioned here as sort of communication channel opens up with outside, and then based on user preferences, you may give different instances of their pictures or their even metadata or the numbers that they did to different people in the outside world. We did a little bit of user acceptance study on this with some researchers, psychologists from Philips Research, and there were two different populations of teenagers and working adults. Teenagers in Palo Alto, working adults in Netherlands. In the Netherlands, we found out, as we expected, that many people are interested or don't mind sharing their body shape avatar, what we call body shape is what we call as a semi-personalized avatar, which may have the proportions of your body, but doesn't show your face, your clothing. It's much less personal information than raw video. And then we have also a skeletal avatar, which has almost no representation of your appearance except your actions. And raw video is obviously an option all the time. Maybe you want to share that with your trainer or coach, but with friends, you maybe happier with a semi-personalized avatar like body shape, and then with outside or unknown people, you may want to only share a skeletal avatar. And this was pretty much aligned with what we observed from a small user study that was done. So how we do it, we have to also be reactive to the user's pose in real time. And we have a single webcam looking at the user from top of a computer or TV screen. And we have been using silhouette matching, basically to have efficiency for real time. And then we have hierarchical search between silhouettes. One contextual information that is available to us is we know what exercise the user is expected to do. That pretty much restricts the search domain in the huge silhouette area that we have to look for the user's pose in a certain instance. So we use that to our advantage. Another notion that's used here is to, when you ship this kind of system, you have to put some data set in there. And we have a so-called generic silhouette set that goes with the system. And based on the initial stages of playing with the system by the user, we may and given instruction to do a certain action, we have an opportunity to acquire a good silhouette from the user. And what happens here is that each one of those silhouettes, after doing some validation and evaluation, is put on top of the generic silhouette, or so to speak, to replace it. So in the next instances of looking at our user, we hopefully have a better chance to see him and decipher his pose based on his real appearance or her real appearance. And then again, a bigger picture would be is a subject of current work, is to extract user behavior model out of these observations, to accumulate history of the exercise that the person did, to correlate with prescribed action that maybe the trainer was suggesting, and then generate further instructions, sort of put the user into a game that evolves with his progress over time. Let's look at, I'm going to show a couple of videos. This is how the user interface looks like. There is a video coming in, the person sees himself here, avatarization happens in the big picture here, big part here, which is sent to the other viewers. And then there are some local measurements of count, speed, pace, and some options for controlling the type of the avatar from body shape to a skeletal, to change the clothing type, some sort of fancy features. And then also to select the build, the size of the body, and people can do this. Or in the future, what can be done also through the eyes of the camera, we can extract the size of the person and map it there. So it's not happened so far, but right now it's selectable by the user. We allow the users to do that. And here is an example of such a method that runs on this same laptop, which at the same time is also running a screen capture. So there is quite a bit of flicker and slowness in the operation. We are doing a few frames per second, maybe 2 or 3, 4 frames per second with this computer, which is from a year and a half ago. So there is hope that we may be able to do this in real time with good number of frames when we have maybe a next generation of processing power available to us and not running the screen capture at the same time. And here's the idea of bringing the second avatar from somebody else that stands next to you. So the user would see himself here, and then maybe a friend or a trainer that shows him what he may want to be doing as the next exercise action. So let's move on to, please stop me at any time if there is any comments, suggestions, or any questions. I'm really eager to hear, to get some feedback from what may be interesting or what may be missing some of these developments that you guys may have some ideas of. Now the notion of user adaptation, we try to take it to a sort of to the next level, basically, by trying to look at the house of a person and try to extract preferences, behavior models, and also location and activity of the person as a context to control things around their house. And we started by looking at the light control situation, which aims to minimize the cost of energy, the usage of energy, while giving enough comfort based on what the user is doing or is perceived to be doing from the eyes of the camera. And here's how we put it together. This graph shows different utility functions. We assume that when somebody is walking, they may want certain amount of energy on top of their head or in front of their footsteps, which you can also measure. Or when they are sitting down, maybe they are studying, we want to provide more lighting. When they are lying down, reclining, we provide less light level. So they're very simple utility functions we put together at design stage, and sort of one solution fit all situation here. What happens in the camera's side would be to extract very simple features of their views, and could be like a bounding box extraction. The aspect ratio of the bounding box would give us some hints about the pose of the person. The communication between the cameras is very low bandwidth, only a few information from the bounding box is sent between them. And then the central aggregator or processor would look at all the received data to try to solve the location problem for the user in the environment, and also have a fused estimation of the pose activity of the person. One good thing here is we don't need to really do this on a frame-by-frame basis. You don't want to turn lights on and off 30 frames per second. These are sort of issues that, as a vision processing algorithm designer, you don't consider. You want to be exact in every frame that you extract information from. But in a real application, there's sometimes much more flexibility that we should use in terms of how much processing we want to do, how accurate we have to do. Do we have to be within 1 inch of the person's location? Should our calibration be that accurate? Or maybe in our application we can be still very well in the OK side if we are plus minus 1 foot from where the person is. And this shows some examples of a person walking, sitting down. Here she's studying, and then somebody lying down. We provide different levels that are shown by the size of the circles and their lighting sources assumed on top of the environment. The other thing is when you change lighting, your camera processing also is affected. Illumination change is a big issue for a lot of vision algorithms. But again, in this case, we know they're going to change the lighting level from certain level to another level. And the simplest thing to do would be to shut down your processing for a few frames and then have your cameras on again and do from that moment on. You don't want to change the lighting again in those few moments anyway, and to use that information. Now, the question we asked after that was, okay, this is a good thing to save energy or be a little bit sensitive to users' context, but we are not adaptive. We are giving one solution that would fit all to our user. And maybe they want to play with the utility function. They don't want too much light when they are maybe watching TV, things like that. Can we create a little bit of adaptive system while being aware of not going full-fledged towards fully automatic system, which we had in the previous case, but at the same time not to ask the user every time that we want to reduce the light by 5%, we ask them, do you like it or not? Maybe we can allow for the user to, whenever they like, they come in and give us some information. And we take that as either explicit input from the user when they proactively change a setting, or maybe when they reach out and when they leave the area, we'll use that also as implicit feedback that they didn't like this kind of music or pattern that we created for them. The applications that we added on top of energy efficient light control, we wanted to also create sort of ambience and multimedia effects. There's ambient music, which has its own attributes, features and values associated with them. You're going to see some of these in a few moments. And then digital window. We are using a lab that doesn't have a window to the outside world, and we try to create sort of a view for the person to look outside, to see some patterns, basically, in a simple way. It has also its own feature set. So this is a reinforcement learning that we have put together by sensing the user's state, which is time of the day, location, and the activity, and we're going to see what kind of activity we're interested in. There's a feedback loop that the user may use, so we don't have to have the feedback, but if they say like or dislike, we take that as explicit feedback. And then we have a Q-learning method that works through these observations and feedback from the user over time to create a map of what he or she likes and what he or she may not like. Then the actor creates either this music jukebox is connected media player, or a PowerPoint projects a pattern of light, moving patterns on the wall. And you give the user a handheld device to provide that kind of feedback. So whenever they like, they can give us some information. Everything is put together through a network that I hope I can show it this moment. This is a live view of the lab at this time. I don't know if you can see those pattern of the stars twinkling. Frame per second. Let me maybe log in again and just to make sure. Okay, yeah. And let's see, there's also supposed to be some music that my students were playing before I came here. See if it's still on. Okay, so, and then we also have this very simple but controller here that, let's see if I can try this pattern here. Maybe, yeah, well. So it could be like a cloudy sky that you may want to look at, or maybe close your eyes and listen to the music. Let's go to pop, maybe it's exciting. There's a rough 11 seconds delay in how we stream audio. Video is much faster, turns out, than audio in this case. In the meantime, change this to an aquarium example. Yeah. So hopefully soon we're gonna hit some pop music. Yeah. Let's see.
So is this a camera from the room we're seeing, or is this simulation?
This is a live feed from the one of the webcams that we have. Yeah, it's a live feed from there. Yeah, it's transferring. Let's ambient and calm perhaps a bit more appropriate. And yeah, sometimes we don't want to create too much noise in the hallway. That's a very narrow hallway up there, and people are not used to having music in third floor of Packard building. So, well, usually we try ambient and calm, and I don't know if this is going to work or not, but and continue, and it comes in, it will come in. Yeah. So then the sensory motor, the part that is also running real time, looking at the person, at our user, it tries to classify the activity into different simple ones like standing, walking, sitting, lying, or maybe more elaborate ones like eating, reading, and watching TV, watching the TV here. Location semantically labeled as kitchen, hallway, dining area, and TV area. And then time of the day is obviously available. Then that would create a state of what is the kind of context at this time for the user. Reinforcement learning, you may be familiar with it. We use a learning factor and then some epsilon, which is exploration factor. We tend to not finish assume the convergence as finished, and we always want, in this case, try to introduce some randomness in whatever we offer to the user from time to time in order to have this opportunity to explore the different dimensions of the user's mind or preference set that we may not have been exposed to. So there is this notion of exploration versus exploitation, how much that information that we have learned from the user we put in a fully exploitable way into the action, or maybe we want to leave some room for exploration of sort of this mutual discovery. So while the user is getting more familiar with how the system works, maybe their behavior also changes. We want to also be able to track some of that behavior change. Also, we try to mimic a human-like behavior, meaning from time to time, even though we are mostly reliable, but not 100% predictable. So we try to introduce some sort of randomness into the services from time to time. And this ongoing activity, ongoing work, we try to improve in all of these aspects, from activity recognition to adaptation and studying what kind of learning methods would be more advantageous. And the next, so we have two more examples. One is not related to homes, but is could be a very personal assistant that some of us may want to use as a speaker when we go to give a seminar or talk. We may want to do some sort of gesture control of our content, not using certain gadgets. Or we want to maybe videotape these seminars and then go back home, watch them, maybe self-evaluate and maybe score ourselves. Or sometimes we go to like Toastmasters events and get some feedback, how well we did, what kind of gestures we could have done better or shouldn't have done and such. So we try to put together some high-level reasoning and intention anticipation of the user into the first instance, and then sort of behavior modeling that is controlled by the user. As user in this case would be the person who arbitrates what is good and what is not good of his own or her own behavior. So there are two times: the user experience part, which is a reactive and real-time gesture, and then analytics part. And I'm showing this because it could be a more general situation when multiple people are in teleconferencing situations. Each one can have their own personal private system to evaluate and use their gestures. So here is an example of what we put together as, again, a real-time system that runs different types of vision algorithms based on what we perceive as the intention of the speaker. And we switch, to be real-time, we have to really run one maybe algorithm at a time. For example, motion detection, face detection, and some hand movement detection. Those things, if you run all of them at the same time, then the laptop will sort of hiccup and will not be able to deliver. And what we also observe here, while this goes on, is a lot of times we are very interested in creating adaptive systems, solutions. But one thing some of us may not pay attention enough to would be that people also adapt to the systems. And as soon as we're going to see, well, right now the speaker is using hand gestures, sometimes with both hands even. But the system doesn't react at all in this case because it knows that she doesn't have any intention to change content. And as soon as she starts to point towards the screen, that's usually what we do as speakers. We look at the screen and then we start having like a laser pointer on. So in this case, the system recognizes based on two events acting as a lot of context for each other. Gazing at the screen and then certain hand movements are recognized, and then that dot is put digitally on top of the PowerPoint. So there is no laser device, any laser pointing device or anything. But then the other thing, I don't know if you noticed, as soon as she sees the first instance of the pointer, she quickly brings her hand down to point to the center of the picture. And that's the part that we call sort of user to system adaptation, which a lot of times as vision algorithm designers, we tend not to use that kind of flexibility and freedom that may be available to us. She also does, there's other gestures for changing pages, which we may or may not want to necessarily use, or different gestures could be appropriate for different situations. Extension to that notion, now if we have this video taken from us, single camera, our own webcam, our own laptop computer, we go back home, can we sit down and try to score and have a systematic method to do it? For example, the use of hands, face orientation, distribution towards the audience, standing pose, and walking pattern. Those things, very simple things, but put together, they define a body language of a person. Can the user himself, in this case, be the judge for what is good and what, for example, not so good, and like scratching one's back of the neck or something. These are very difficult to define as again algorithm designer. How do you score this as good or bad? Maybe somebody really benefits from walking and talking because could maybe a mathematical discussion, and then walking can help keep the focus of the audience. So we should let them, the speaker, to be the judge in certain situations and give us the value metric definition actually. So here it shows that this notion is not standing alone. It can also be connected to the notion of smart documents that they go a little bit beyond whatever PowerPoint produces or provides today. What will be like points of emphasis, transitions between slides, interactions with the audience, how they can maybe change the content of the slides automatically, how to zoom in, zoom out, and magnify certain parts. And then maybe the history of what the user did in giving the similar talk maybe a few days ago can come in and help the system to run more efficiently, or the experience to be more pleasant to both the users and the audience by giving some hints to the speaker that you may want to point out or do certain gesture, or maybe avoid too much walking at this point because it was distractive last time, things like that. So what we're doing, again, in practice would be we look at the head trajectory of the person. Again, these things can run in real time. Try to encode the global movement. You can look at face and head orientation for eye contact, and then near body movement to encode some use of hand. And again, we can classify semantically if the speaker looking at the sky, looking at the ground, and different angles. But then the big notion here is to give the user a self-evaluation authority, to sit down, go through these episodes of like 1 minute or half a minute each, and then try to score between like 1 to 10. Is it good or bad? Good or bad? And then vision processing works in the background, extract those elementary features, and then goes through a sort of a scoring function learning to decide what would be the good behavior eventually and what would be the bad behavior as defined by the user. And one good thing about this system is it's very private. You don't have to bring a specialist to sit down and look at it and tell you whether it's good or bad. You can score, and then the system at the end is a very private, and that's one of the notions of using cameras in a kind of creating privacy. Sensitivity for camera networks would be to give the users maybe all the information, and then nothing would be sent to outsiders. Examples of which features that are used, you don't have to go through them. And then finally, here's an application that tries to combine a bunch of these notions from use of multi-cameras, camera priors, big part in high-level reasoning, how to interface what comes out of vision processing into a big probabilistic logic engine, and try to make interpretations over time that are supported by further observations. That means they become more and more confident over time. And we talk about this in the realm of object recognition, which is also a classical vision problem, still an ongoing research paradigm, where a lot of works are centered around big training sets of like things that look like chairs or sofas, and then by doing training and testing and evaluations, we can see that sometimes these methods fail, and then because the set was not updated. So when there is a new design for a chair, we have to update our system and run the training again. Additionally, many objects may not be really relevant or used by our user at their home environments. Maybe they use some objects more often, and we want to create those lighting instances for those when the user is in proximity of those objects. Or the user may use different objects in different way that his demographic counterparts may use. For example, somebody may want to sit on a table, not on a chair, when they're watching TV. And this object is a good example, and we can all guess what this might be. And I don't think any chair classifier can take this out as a chair or a sofa. And there it is. So it's a new design for a chair. And again, as soon as we see one instance of a person sitting on it, then we may have a chance to declare it correctly. Otherwise, with traditional object recognition, it's going to be pretty challenging to classify as a chair. And then as a byproduct of this method, by looking at what the user does, the user-centric approach with his or her objects in the home environment, we can also try to extract a behavior model for his actions over daily routines. Simple example would be when we look at we want to discover where the floor is. We look at one episode of a video, and then we pretty much can tell by doing some segmentation and combining these. We can tell where and then also similar for doors and simple stuff like that. But the question we raised earlier was how to create a systematic way of reasoning that can also handle much more complex situations, such as the ones here, for example. If the user, we know the context is a kitchen, and then we see the user taking something out from one location, put them in another location for maybe half a minute, waits there, takes that out, and goes to the dining area. Can we start to infer there may be a fridge microwave pair involved in this action? Or when the user is sitting down and we have a period of gazing or watching, can we infer there's going to be a sofa, coffee table, and TV involved in that location? So trying to purely going after orthogonal method to appearance-based object recognition by looking at only user-based user interaction-based semantic labeling of objects. And you can see the situation can become pretty complex when we have many different objects, activities, poses, and sequences in time, and also relationships in the spatial domain, things that are used concurrently. So here's how we put the starting to put the probabilistic model together by going to first order logic that is supported by certain soft weights. And Markov logic network is a tool, is a graphical representation method that provides that option to define rules that are not 100% certain, and also play with observations that are also not 100% certain. So when vision processing happens, it may give us a probability of maybe 0.7. Sometimes we even don't have access to this kind of confidence level. We just churn out some number or some pose that the user is at, which may or may not be correct. Meaning we don't want to make decisions immediately on those and act on those frame-by-frame information coming from vision processing. So this sort of ecosystem is used to handle uncertainty in our observation as well as uncertainty in our common sense rules and logic. And let me go through this quickly. We have been looking at some sequences, obviously, to test the algorithms. This is what we talked earlier. We used that bounding box prior information right here in order to get rid of some of the outliers. And we can see from every frame, every few frames, you're going to see an outlier object that you don't want to use. And then there is also another prior that we use, that performance of past pose classification by cameras are recorded. And based on what the outcome of those reports were, we can assign priorities to different cameras when they declare certain pose. For example, in this case, the camera looking at this angle, declaring a lying pose, is much more reliable than the one that's looking from behind the dining table. Same user, same pose, but the user is not seen very well there. So that's another contextual information we use. We do this CRF, conditional random field processing, which links information over many frames of in each camera. And then additional poses that we are working on and using context with would be when user is in proximity of certain objects in the environment. So it's like a iterative method that if we have information about a certain furniture being somewhere, we use that information to go into more detailed description of the person's action, like eating or watching the TV. And let me show a couple of examples and finish by looking at this bar chart that shows what is detected as the camera network's output as the pose of the person, which is standing, sitting, and reclining, or no activity or no report. So we saw the user was standing somewhere and then she sat down here. When we saw standing, the probability of this location being a floor, and this is happening for a single grid on this map, starts to increase. And as soon as there is a sitting activity observed, we're going to start increasing the probability of this may be a chair or a sofa. And after a while, we have an opportunity to see the user lying down there. And that quickly reduces the probability of this location being a chair and increases the sofa-ness of that location, because we have these rules embedded in the logic. Similarly, when she's watching the TV here, and then we increase the probability of this location to be the TV, which is not actually correct, because in this case, we have no way of deciphering exactly where the line of sight would land. We only see that there is an angular orientation from the sofa towards this wall. But thankfully, later on, we see the user walking over this block of grids, and then we can immediately turn off the TV-ness of that location and raise the probability of this being a floor. So rules have different ways, and that's how we are using the weighting function to control how decisions are made when rules are in conflict, observations are in conflict with each other. And similarly, when happens vice versa, let's look at this video that sort of summarizes what we just talked about. When we see dark grids, those are the ones that are assigned higher probability of being labeled as those semantics written up there. Floor, chair, sofa, TV here, and there's no observation of TV in this sequence. So we have a few chairs and sofa here to declare. Then when the user sits down and watches the TV, then we have an option to observe or semantically label some of these pixels to be associated with the TV. And then there's going to be a lot of inaccuracy in this, and views are pretty small. We can even not see the eyes of the user, but by looking at the duration of gazing, we try to infer that there must be something interesting on the wall going on for her to look at. So we increase these probabilities, and all of a sudden there is a second instance of, here she's studying, and then she reaches out for the remote control to watch the TV again. And then we are a little bit confused here about this. Some of these pixels are redundantly labeled as being TV. As soon as she walks out from here, then we're going to sort of erase those probabilities as we get more information. So extension would be to link these events in the kitchen context when, as I mentioned, examples happen. The person takes stuff out and eats and brings them back to the sink. We have been able to label some of these fridge, dining table, workspace, and sink between the kitchen and dining area. And that's ongoing work, obviously. We need much more to be written and done. The question we're asking at this time is whether we should stop at some point. Is there value to query or ask the user for validation? At what point we should do that so we don't bother the user too often? And when we do that, should we, how to score that user input? Should we take it as face value, or there maybe still some probability that the user gave us some wrong indications? Maybe he or she is an experimental user wanting to know when the system breaks down. So there's going to be potentials for putting rules here that also embed some of the user's explicit input to the system. And that brings us to closer to the area of interactive machine learning, how to use human in the loop into our design. Open questions, and just to finish, I'll stop on this slide, which summarizes the whole picture actually, from vision processing, access to toolbox, to high-level reasoning, which keeps a placeholder of all the accumulated knowledge from behavior, from the environment, from the user, from how we adapted to the user. And then we can see that on the context layer, we can try to build up models for almost everything, for our user, for the environment and what is in it, for how the cameras behave inside the network. And then obviously we can try to infer normal, abnormal classification activities over time. And there's obviously this is what we emphasize throughout the talk today, how to bring that contextual information back towards system level intervention or helping the cameras, task assignment, dispatching, to signal level, which processing to choose, or how to combine information, and then also to semantic level, how much of that additional context we want to embed and encode into our contextual box in the high-level reasoning. Let me finish here. And
there's a class right after this, so if you want to ask questions, come out in the lobby here, and you can ask questions.
For more, please visit us at stanford.edu.